Hi Travis, hi Wayne. This is our 12th video lecture for the probability graduate level class. And last time we talked about two random variables being independent and what that meant about their joint PDF or joint PMF being equal to the product of their individual PDFs or PMFs. And today we're going to look at some examples trying to determine whether two random variables are independent or not. And then we're also going to move on to covariance. And then we'll get a fact here at the end about something defined to be convolution, where we're adding two random variables together and looking at their joint PDF. Okay, so let's go ahead and get started about trying to determine whether two random variables are independent or not by looking at their joint PMF or joint PDF and see if it's the product of individual aspects of the random variable. So here's an example. Let's let f of x comma y equal to 1 over 30 x squared times y, where x is equal to 1 and 2, and y is equal to 1, 2, and 3, be the joint PMF of two random variables. X and y. And of course, they're discrete random variables. And the question is, are x and y independent? And the way we're going to answer that question is by determining if the PDF for x times the, PMF for x times the PMF for y is equal to this joint PMF. Okay, so we need to calculate the PMF for y, for x, let's start with that. So f of x, and what that is, if you remember, is the sum over all y days, so that's y running from 1 to 3, of the joint PDF, f of x comma y. Here, I'm just going to set over y values and then get a little bit more specific here. This is the sum as y runs from 1 to 3 of 1 over 30 x squared y. Let's see. Y runs from 1 to 3 of 1 over 30. The x squared is also a constant with respect to y, can be pulled out. And what we're having is 1 plus 2 plus 3. That's 6. So we end up getting 6 over 30 x squared, which is the same thing as 1/5 x squared. So that is the PMF of x. Now we'll compute the PMF for y. Similarly, so we're denoting that f sub y of y is equal to the sum of the x's of the joint PMF, and the x values, of course, in this case, run from 1 to 2, and then this is 1 over 30. It was x squared y, and then the 1 over 30 can be taken out as a constant, and here we have the sum as x runs from 1 to 2 of x squared. That's 1 over 30 y. Here, when I let x be equal to 1, I just get 1 squared, which is 1, 2 squared plus 2 squared, which is 4. So I end up getting 5 over 30 y, and that, of course, is equal to 1/6 y. Now, here's what we know. Note that f of x times f sub y of y, well, that's equal to, so f sub x of x was 1 over 5 x squared, where the x values run from 1 to 2. And then f sub y of y that is right here. It's 1/6 y, and that's equal to 1/30 x squared y, which I will say, which equals to f of x comma y, where x is equal to 1 and 2, and y equal to 1, 2, and 3. And so since the product of each individual PMF is equal to the joint PMF, we have that x and y are independent. Well, that was an example where we were talking about two discrete random variables. Let's look at an example next where we're talking about two continuous random variables. Okay, so it's a little fuzzy, there we go. So, for example, for the continuous one, another example, we're going to let f of x comma y, this is something we're familiar with, an example, be defined by 5/16 x times y squared if we have 0 is less than x is less than y is less than 2, and 0 otherwise. This is, that be the joint PDM of x and y. And the question is, are x and y independent or not? Okay, so here, let us remember where the joint is defined to be non-zero. It's the x values run from 0 to 2, the y values run from 0 to 2. And then if we look at y equals x, that's this line, and it breaks up the square into two regions, and it turns out the region within that square where x is less than y, we've done this before, where x is less than y is this top region. So that's what we're in there. So here, we'll note that f sub x of x, the PMF of the random variable x, what it's supposed to be equal to is from infinity to minus infinity of the joint dy. Now, now the x values, they run from, in some sense, from 0 to y, 0 to 2, I should say. Okay? That's what they run from 0 to 2. So here, this ought to be the integral from 0, for each x value, I'm sorry, each x value can run from 0 to 2 here in this case. But for a fixed x value, what does a y value run from? Okay? The y values will run from that line, which is x up to 2. And so here, this will be 5/16 x y squared. This is dx, I'm sorry, dy. That's what we have. And let's see, that's going to be equal to, so it's going to be 5/48 x y cubed, that's the antiderivative for 5/16. So I'm just adding 1 to 3 and dividing by the adding 1 to 2 and dividing by the new power of y. And I need to evaluate that from x to 2, those are y values. When I do, I get 5/48 x times 8 minus, when I stick an x, I get 5 over 48 x to the 4. And that can be simplified, that 8 goes into 48 6 times. So 5 6 x minus 5 over 48 x to the 4. The next values are running from 2. Okay, let's find out about the y values. For the PDF of y, that's going to be equal to, it's an interval from minus infinity to infinity, f of x comma y dx. Again, let me draw the picture for the joint where it's non-zero. So looking here, and for a fixed y, y is somewhere between 0 and 2. So for a fixed y, the x values will run from 0 to y. So this is n equal to 0 to y, that's what the x values will run from. Here this is 5/16. It was xy squared dx. Antiderivative for this is 5 over 32 x squared y squared, evaluate from 0 to y. Again, these are x values. And so when I stick in y, I get 5 over 32. This will be y to the 4th, and when I let x be 0, I just get 0. So that's what I have. So here's the thing to notice. No, f sub x of x times f sub y1 is equal to 5/48 x to the 4th minus, 5 6. No, it's 5/48. No, 5 6 x. Now I'm looking at the right spot. Minus 5/48 x to the 4th times the f sub y is 5 over 32 y to the 4th, and that is not the same as the joint. That's right. So, x and y are not independent. They're dependent. They're dependent random variables. Okay? So those are two examples where we're trying to determine whether two random variables are independent. Okay. Next thing I want to look at is a fact. And the fact that I want to look at is having to do with independence. Here's what it says. It says, if x and y are independent random variables, then for any functions h and g, the expected value of g of x times h of y, so g is a function of x and h is a function of y, That's equal to the expected value of g of x times the expected value of h of y. So we can prove this in the two cases that we're going to look at, but I'll only do one of them, is that we'll start off by letting x and y be independent random variables. So case 1, so case 1 is where we'll say, suppose x and y are continuous random variables. Okay. Then the expected value of g of x times h of y. We could think of this as a function here of the random variables x and y. And so the expected value is going to be the interval from minus infinity to infinity, minus infinity to infinity, of this function, which I'll rewrite as g of x times h of y, multiplication of the functions. And then here we have the joint p df, f of x times y. Now write down dx dy. So that's the way that we define. And then, because of the independence, we can rewrite this joint PDF as the multiplication of the PDF of x times the PDF of y. Okay. Now look, we're supposed to be doing dx first, but h of y doesn't have an x, and f sub y doesn't have an x in it. So we can pull those out of the first interval. And what it's going to do is produce the following intervals. So here I'm going to have h of y, f sub y of y. Then, if you will, this inner intervals from minus infinity to infinity of g of x, f sub x of x dx, and then dy. Now, this inner integral is really just a number, and as a matter of fact, what number it is, is the expected value of g of x So I can write down the expected value of g of x if that is a constant, pull it out. Of course, we're assuming the expected value of g of x is a finite number here. The expected value of g of x is a number unless it's infinite, okay? So we're going to assume that it's a finite number. Here, it's interval from minus infinity to infinity. This is h of y, f sub y of y, dy. But of course, the second interval is nothing more than the expected value of h of y. And so that proves the statement in the case where x and y are both continuous. And so case 2, if x and y are both discrete, then the proof, I'm not going to do it, works analogously to case 1, except we have summations instead of integration. And that's what I'm going to say. It's the proof. Okay, so I'll leave that second part to you. Okay, the next thing we want to do is to find a new topic, sort of, based on the interplay between x and y. It's called the covariance of x and y. So here's the definition. Let x and y be random variables. Then the covariance of x and y is denoted by COV of x comma y and given by the covariance between x and y. What it's equal to is the expected value of the quantity x minus the expected value of x times the quantity y minus the expected value of y. So that's somewhat similar to the variance, okay, of one random variable. We'll see a connection in just a few minutes. As a fact, the covariance between x and y is the same thing as the expected value of the quantity x times y minus the expected value of x times the expected value of y. Look, I'm going to prove a fact a little later on, but about related covariance of x with x. Same thing as the variance of x. But you see the covariance has a formula that's very similar to the variance. So remember the variance of x was x squared, which was the expected value of x squared, which is x times x. So here when we got two different random variables, we multiply them together. And then remember in the variance formula for x, the last part was the expected value of x times the expected value of x. Here we have the expected value of x times the expected value of y. Well, let's prove this. And we'll break it into cases. So case 1, we'll prove when x and y. Well, I don't have to prove it in terms of x and y being different things. Here, we can do it all at once, I think. We could break it up into x and y being discrete, x and y being continuous, but instead, let's just do it this way. Here, note, let's see if we can do it this way. The covariance of x comma y is equal to the expected value of x minus the expected value of x, where we're thinking the expected value of x is a finite number, times y minus the expected value of y. Well, let's do the multiplication of those constants. So here, this is equal to the expected value. So we multiply this out. What we have is x times y, I think, minus x times the expected value of y. Then it would be minus y times the expected value of x. And then it would be plus the expected value of x times the expected value of y. Now, whether you have a double integral here, you could think of this, what we're taking the expected value of, is a function of x and y. And so whether you're taking the double sum or double integral, what you can show is that this is equal to breaking this up into the expected value of x times y minus the expected value of x times the expected value of y minus the expected value of y times the expected value of x, and then plus the expected value of the multiplication of the expected value of x times the expected value of y. Now, the expected value of x times y, that's what we have. Here, the expected value of y, we're considering it a constant, so I pull it out. So that's the expected value of y times the expected value of x, still left, minus the expected value of x constant, so I'll pull it out, expected value of x times the expected value of y. And here, the expected value of x and the expected value of y is a constant, so its expected value is just the expected value of x times the expected value of y. This is equal to the expected value of x times y minus 2 times the expected value of x times the expected value of y plus the expected value of x times the expected value of y. And then, of course, these are like terms, so we end up getting the expected value is equal to the expected value of x times y minus the expected value of x times the expected value of y. So I'm going to say that's good enough for the proof. And we're using some properties of expected values here that I might get you to provide the details for in a homework assignment. Okay, we should do examples where we're computing the covariance. That's what we'll do next. So as an example, we're going to let f of x comma y be equal to 1. And that's if 0 is less than or equal to x is less than or equal to y is less than or equal to square root of 2, and 0 otherwise. And then we want to find, so let this be the joint PDF of x and y. What we want to do is we want to find the covariance between x and y. I'll just say find covariance between x and y. Okay. So I'm thinking of this as having 3 parts. So I'm going to say note the covariance of x comma y is equal to, by what we've just proven, the expected value of x times y minus the expected value of x times the expected value of y. Okay. And so I said it's got 3 parts. We've got to find the expected value of x times y, we've got to find the expected value of x, we've got to find the expected value of y. Okay, so here, note the expected value of x times y. That's a function of x, y that's been multiplied together. This is a continuous situation, so we're going to have a double integral. So from minus infinity to infinity, minus infinity to infinity, of x times y, f of x comma y, dx dy. Okay, where is this PDF non-zero? It's non-zero along the xy plane.
in between where x runs from 0 to square root of 2, and y runs from 0 to square root of 2, and then that x being less than or equal to y. Again, we're given a similar situation as the example we had before, and that it's this top prime. And so, if I want to describe this, I'd say, well, we're doing dy last, so that's 0 square root of 2 is what the y values run from. And for any fixed y value, the x values run from 0 to y. And here I have x, y, f of x comma y over that region that I'm integrating right here, over that region, is just defined to be 1. So then I have dx dy. Okay, we do the antiderivative of x, and I have this first interval, 0 square root of 2. The antiderivative of x, y with respect to x is just x squared over 2y, evaluated when x runs from 0 to y, and then whatever I get for that, I have to integrate with respect to y. Now, doing that evaluation, we stick in y for x, so it becomes the integral 0 square root of 2, y squared over 2, and then when we let x be 0, oh, it's not y squared, it's y cubed over 2, and then when I let x be 0, we just subtract 0, we get 0. And so this is dy. Taking the antiderivative of this, I get y to the 4th, and so I pull out, or divide by 4, and I will evaluate that from 0 to square root of 2. So here, I stick at square root of 2. Square root of 2 raised to the 4th power, that's the square root of 2 to the square root of 2, and then I do that again, so I get another 2, so it's 4/8, and then minus, when I let y be 0, I get 0, and so we just get 1/2. So that's the expected value of x times y is 1/2. That's what I got previously. Note, the second thing I'm going to find that I need for the formula is the expected value of x. This can be thought of as a function of x and y. It's just x. Okay. So here I integrate from minus infinity to infinity, minus infinity to infinity of x, and then f of x comma y, dx dy. Again, the f of x comma y is 0 most of the spots, so it becomes the interval from 0 to square root of 2, 0 to y, of x times 1 dx dy, and that's equal to the interval from 0 to square root of 2. Doing the integral, I get x squared over 2, evaluated from 0 to y, dy, that ends up being an integral from 0 to square root of 2, y squared over 2, when I stick in 0, I get 0, dy, and then here, this is equal to y to the third, the antiderivative, y to the third over 6, evaluated from 0 to square root of 2. Now sticking the square root of 2, I'm going to get 2 times square root of 2 over 6, minus 0, which equals to square root of 2 over 3. So that's the expected value of x. Now, let me make sure I didn't make a mistake. I did. Now let me find the expected value of y. The expected value of y, well, again, we can think of this as a function of x and y, where we'll just get out y. So I write down a double interval of y, f of x comma y, dx dy. And that's equal to, well, 0 to square root of 2, just as we had before, 0 to y of y, and this is 1, dx dy. That's going to be yx, integral from 0 to square root of 2, antiderivative of y with respect to x is yx. I've got to evaluate that from x running from 0 to x running from y. And then that dy, that's equal to the integral from 0 to square root of 2. When I let x be y, I'm going to get out y squared. When I let x be 0, to subtract from it, I'm just going to be 0. dy. This is an easy integral to take. It's y to the third, so by the power rule, we add 1, anti-power rule. We add 1 to the power, divide by the n power, and we evaluate that from 0 to square root of 2. This ends up being 2 times square root of 2 over 3. Times square root of 2 over 3. That's right. So, covariance of x times y is equal to, again, the expected value of x times y minus the expected value of x times the expected value of y. And these numbers, if you remember, I've got it written down here. It's 1/2 minus the expected value of x, that was the square root of 2 over 3. And then here, this is 2 times square root of 2 over 3. So that ends up being, we're going to get a common denominator of 9. No, I think the common denominator is going to be 18. So it's 9 over 18 minus, here, this is going to be square root of 2 times square root of 2 is 2. 2 times 2 is 4 over 9, so it's going to be 8 over 18. So I end up getting 1 over 18. That's the scope. Let's look at another example, a Greek one. So here's an example. We'll let f of x comma y be equal to x plus y of 21, where x is equal to 1 and 2, and y is equal to 1, 2, and 3. This is an example we've seen before. Be the joint PMF of x and y. Here, we're going to find the covariance between x and y. So, again, we know the covariance between x and y is going to be equal to the expected value of x times y minus the expected value of x times the expected value of y, so that's by this formula, that's what we use. The expected value of x times y is what I'm going to calculate first. And so this is the expected value of a function of x and y. Well, that's equal to, because we're talking about discreteness, it's the sum, I'm going to write down as x, y. It's x times y, f of x comma y. But this f of x comma y is 0, except when x is equal to 1 up to 2, and y runs from 1 to 3. This is x times y, and then this will be x plus y over 21. Okay. Okay, well that's equal to, so when x is 1, here's what I'm going to get. I'm going to get 3 terms. When x is 1, I'm going to get, x is 1, so y will run from 1 to 3. When y is 1, we'll get 1 times 1, and then 1 plus 1 is 2 over 21. Plus x is 1, so y is 2, so I'm going to get 2, x times y is going to be 2. And then here this will be times 3 over 21. plus, when x is 1 and y is 3, I get 1 times 3, that's 3 times 4 over 21. Excellent. That's what I get in this double sum when x is equal to 1. When x is equal to 2, we're going to get 2, and then y runs from 1 to 3. When y is 1, we're going to get the multiplication to be equal to 2, and then here, x plus y will be equal to 3 over 21. Now, when x is equal to 2 and y is equal to 2, we get 4, x times y is 4. And here we have 2 plus 2, that's 4 over 21. And then finally, when x is 2 and y is 3, we get 6 for the multiplication of x times y. And then 2 plus 3 is 5 over 21. And so, let's compute what this is. So this is 2 over 21 plus 6 over 21 plus 12 over 21 plus 6 over 21 plus 16 over 21 plus 30 over 21. Okay, so this is 30, 46, 52, 54, 64, 70, I think it's 72 over 21. And definitely that can be reduced. 3 goes into both of them. It's 24 over 7, and that's the previous number that I got when I worked before the lecture. Note the expected value of x. Again, I can think of this as a double sum. So here it's x runs from 1 to 2, sum as y runs from 1 to 3. I'm going to skip a step here. This is the function of x and y, so I'm going to write down just x here. And then I have f of x comma y, which we know to be x plus y over 21. So that's what the expected value of x can be written as. And as I compute this, again, x is running, we let it be 1 to start off with. And let y run from 1 to 3. Here's what we get. When x is 1, we get 1 times, well, when y is 1, we get 1 plus 1. So it's 1 times 2 over 21. When x is 1, we still get 1. And then y is 2, we have 3 over 21. When x is 1, we still get 1, it's this number here. But this, when y is 3, would be equal to 4 over 21. Plus, now when x is 2, we're going to get 2 times 2 plus 1 when y is 1 is 3 over 21. Plus 2 when x is 2 now. And here's 2 plus 2, that's 4 over 21. And finally, x is 2 still, and y becomes 3, so we get 5 over 21. And when I add these together, I get 2 over 21 plus 3 over 21 plus 4 over 21 plus 6 over 21 plus 8 over 21 plus 10 over 21. And that's equal to 18, 24, 28, 31, I think it's 33 over 21. Again, 3 goes into both of these. It's 11 over 7, I think. That's right. Last thing to calculate. Is the expected value of 1. Again, I'm going to skip some steps and say, look, this is a double sum. X runs from 1 to 2, y runs from 1 to 3. Again, the function of x and y in this case is y, and then it's x plus y over 21. And that's equal to, okay, so we let x be 1, y is 1. So I get 1 times 2 over 21. Plus, x is still 1, y is 2. So I get 2 times 3 over 21. X is still 1, y is 3. So I get 3 times 4 over 21. Now we're going to let x be 2. So y runs from 1 to 3. So when y is 1, we get 1. 2 plus 1 is 3 over 21. Plus, when y is 2, x is 2, we're going to get 2 times 4 over 21. And finally, when y is 3 and x is 2, we're going to get 3 times 5 over 21. So computing
this addition, we have 2 over 21 plus 6 over 21 plus 12 over 21 plus 3 over 21 plus 8 over 21 plus 15 over 21. So it's 23, 26, 28, 38, 44, 46 over 21 is what I got. And that's the right answer. And so here, to do this work, the covariance between x and y, that's equal to, well, it's the expected value of x times y minus the expected value of x times the expected value of y. And so the numbers involved here were, let's see, 24 over 7 minus 11 over 7 minus 46 over 21. And if you work with this, you'll find that the answer here is minus 2 over 147. That's the correct answer. All right, the next thing I'm going to do is some properties. Of covariances, so some properties of covariances. So the first one is the covariance between x and x is nothing more than the variance of x. 2, the covariance between x and y is the same thing as the covariance between y and x. Thirdly, the covariance of a constant times x to y is equal to c times the covariance between x and y. And finally, fourthly, the covariance of x with y plus z is equal to the covariance of x with y plus the covariance of x with z. And we're going to prove each one of these facts. The first are very simple. So the proofs, for one, note the covariance of x with x. So I'm going to use this definition. You don't have to. There's multiple ways of doing this. This is equal to the expected value, not from the fact, but from the definition. It's the expected value of the quantity x minus the expected value of x times, now it's the second random variable, well that's x minus the expected value of x. And that's nothing more than the expected value of x minus the expected value of x to be squared, but that was the definition of the variance of x. So that's part one done. Okay, part two, I'm again going to use the definition. So the covariance of x with y, we want to show that that's equal to the covariance of y with x. Well, this definition is the expected value of x minus the expected value of x times y minus the expected value of y. But this is a multiplication. We multiply two algebraic quantities first times the second. That's the same thing as the multiplication of the second. With the first. And that's equal to the covariance of y with x.
So that ends part 2. For part 3, I'm going to use the fact. And so here, we want to show that the covariance of C times X, where C is a constant, times Y, is equal to C times the covariance of X and Y. Well, by the fact, what this is equal to is the expected value of C times X, and then that times Y, minus the expected value of C times X times the expected value of Y. Well, the constant can be pulled out of the expected value. So this is C times the expected value of X, Y, minus C times the expected value of X, expected value of Y. And then these are two terms that are being subtracted. They have a common factor of C, so I pull that out. And so we're left with the expected value of X times Y minus the expected value of X times the expected value of Y. And that's just C times the covariance of X with Y. Okay, that ends part 3. Let's do the last fact. And we'll use the covariance formula fact to generate the proof. Okay, so for fact 4, remember what we're doing. We're looking at the covariance of X with the random variable Y plus Z. So Y plus Z is like a new random variable, even though it's composed of, made up of 2 random variables, Y and Z. And so by our fact, that's the expected value of X times the second random variable, which is Y plus Z. Plus, this will be the expected value of X times the expected value of Y plus Z. When we multiply this out, we get the expected value of the quantity xy plus xz plus, here will be the expected value of X times the expected value. Now, what we had proven was the expected value of the sum of 2 random variables is equal to the expected value of the first one plus the expected value of the second. So I'm using that fact here. And again, we have something similar. We can think of these as 2 random variables, and we're taking their expected values. So the expected value of the first one plus the expected value of the second one. This will be, I have made a mistake. I said I'm using the fact, but the fact's got a subtraction here. Well, maybe a mistake. Let's put a subtraction. Okay. Now, this is subtraction when I distribute this expected value of X, I get the expected value of X times the expected value of Y, minus the expected value of X times the expected value of Z. Kind of reorganizing these terms, I can have the expected value of X times Y minus the expected value of X times the expected value of Y, then plus the expected value of X times Z minus the expected value of X times the expected value of Z. And then that's equal to, here this is the covariance of X with Y plus the second part is the covariance of X with Z. So that is for part 4. There's one last thing I want to do. Okay. So finally, it's a fact. If X and Y are continuous with
of x being the PDF of x and f sub y of y being the PDF of y and x and y are independent, then the PDF of x plus y, so this is one random variable, I'm thinking of it, is f of x plus y, and I'll say of a, and what's going to be equal to, this is equal to minus, then minus infinity to infinity, of f sub x of a minus y times f sub y of y dy. So that's what we want. Okay, so we're thinking of x plus y as just a random variable. And so here's how we're going to put it. The proof. Let x and y be continuous independent random variables. Note the CDF, cumulative distribution function, of x plus y is, this is big out of x plus y of a. That's why I can rewrite it. So the function of a. And here, what this is the probability that x plus y is less than or equal to a. Now this is we're talking about x plus y being less than a number. So it's got two random variables in it. So I think of it as a double integral where x plus y, so this is my set, is less than or equal to a. Of what? So of what? Of the joint PDF between x and y. All right. But that's equal to, because of independence, the integral over the region where x plus y is less than a of f sub x of x times f sub y of y, because of the dependence of x and y, dx dy. Now let's see what region it is that we're talking about. So here, let's let this be a, here's my x-axis, here's my y-axis. Okay, so let us graph x plus y equal to a. So x plus y, so I'm looking at little variables, equals to a, is the same thing as y is equal to a minus x. When x is 0, y would have to be a. When x is a, y would be 0, so it's got these 2 points on it. And it's this line. Okay, that's one. And if you look at the region where x plus y is less than a, here I'm assuming a is positive, it wasn't still okay. So if we look at the region where x plus y is less than a, if we take this point here, 0, 0, if you take 0 plus 0, it's adds to 0, and that's less than this a, so we must be talking about this region down here. So this interval then can be re-described here as the y's run from minus infinity to infinity. So this region, the y values can go up to infinity and go down to minus infinity.
for each fixed y value, so let's say for this one, what do the x values run from? They run from minus infinity, okay, up to this line. So that's what the x values run from. That's a minus y. So I got f sub x times f sub y of y, dx dy. Okay. So let's remind ourselves where we are. On this other board. So, what we have then is this because of the independence, we're able to break this up into some intervals here. The interval from minus infinity to infinity of f sub y, this isn't so vital. Interval from minus infinity to a minus y of f sub x, here's dx interval, dy. And then this could be rewritten. Remember what we're talking about. We're talking about the CDF of x plus y of a. This is equal to the interval from minus infinity to infinity of f sub y of y. Here, what this is, when you integrate from minus infinity up to something of f sub x, what you're doing is finding the probability that x is less than this. So that's the CDF of x evaluated a minus y dy. Now, if you want to get the PDF from the CDF, where we have a continuous random variable, you differentiate with respect to the variable. And it's about fundamental calculus. And so I differentiate here with respect to a. Okay. Now here, I can bring this integral inside, and this guy is nothing more than the PDF of x plus y, evaluated a. And I can bring, as I said, this derivative inside the integral, f sub y of y, derivative with respect to a, of f sub x of a minus y, dy. And when I do this integral, do the derivative, I should say, of this quantity, what I get is, so this stays the same, this is a y. Here, this is nothing more than the PDF of x of a minus y. By the fundamental theorem of calculus, I have to multiply this by the derivative of the inside chain rule. And so here, this will be the derivative of a with respect to a, but that's just 1, and then dy, and that's what we said. And I'm going to tell you, this is called the convolution of x and y. With y. So that's got a fancy name. All right, that's enough for today. Thank you very much for your time.